Hello everyone, welcome to this lecture of two-phase flow. My name is Mingchang Li. I'm currently a faculty at the Department of Power Mechanical Engineering in National Tsinghua University. Per the request from the university, I'm recording and sharing this series of lecturing for NTHU OpenCourseWare. Today, we are going to introduce some important concepts in modeling nucleate boiling. Most of the features of the classical boiling curve were determined by the works done by researchers like Dr. Nukiyama, Jacob, and Zhu in the 1930s. Here, let's revisit those characteristics and the features of the classical boiling curve as shown on this figure on the left. The surrounding fluid of the heating element is assumed to be at the saturation temperature corresponds to the ambient pressure. The temperature of the heating element at its interface with the surrounding fluid is controlled. The excess temperature is used as the horizontal axis, and the vertical axis is corresponding heat flux at the solid surface to the surrounding fluid. If the temperature of the surface is increased slowly from the saturation temperature of the fluid, Tsat, the fluid near to the surface of the solid will be heated up gradually, and the density of the fluid will be changed correspondingly. Usually, the density of fluid decreases with the increasing temperature. Assuming the direction of gravity is downwards, then the hotter fluid flows upwards due to buoyancy, and the colder fluid sweeps downwards to contact the hot surface. This circulation leads to the typical natural convection, and the heat transfer increases gradually and slowly with increasing the excess temperature. This is the regime between A to C on the boiling curve. As we discussed in previous lectures, the onset of nucleation boiling would start at the point that a sufficient superheat of the fluid near the hot surface is reached. This occurs at the point C on the curve. Since the temperature of the solid surface is controlled, a sudden increase of the heat flux is expected as a result of the newly added heat transfer mechanism due to liquid-vapor phase change. This is shown by the vertically moved curve from point C to D. For water at the ambient pressure of 1 atm, the typical excess temperature required for initiating the nucleation is around 5 to 6 degrees C. After the onset of nucleate boiling, if the excess temperature is further increased, more nucleation sites on the heated surface will be activated. The numbers and growth rate of vapor bubbles therefore increase and result in rapidly increased heat flux along the boiling curve from point D to F. This is the nucleate boiling regime, and apparently is the major section on the boiling curve that is of great interest for enhancing heat transfer by utilizing liquid-vapor phase change. This regime can be further divided into two sections. In the first section, each bubble grows and departs from the nucleate site without significant contact with other bubbles. This is referred as the isolated bubble regime. If the surface superheat is further increased so that more active sites are available, bubble growth rate as well as departure frequency become high enough so that bubbles from adjacent active sites merge together upon release from the solid surface. This in turn makes vapor columns and slugs right above the hot surface. The vapor column moving upwards start to reduce the downward flow of liquid, and the hot surface of the solid is covered more and more by the vapor slugs and separated films. This makes heat being transferred through the vapor film at some locations. Since the thermal conductivity of vapor is usually lower than that of liquid, the heat flux from the surface starts to increase slowly with increasing the excess temperature. Eventually, a large portion of solid surface is covered by vapor columns, and the heat flux from the hot surface reaches its maximum point, which is called the maximum heat flux, or the critical heat flux. If the surface temperature is further increased beyond this critical heat flux point, the transition between nucleate boiling and the film boiling could be observed. The portion between F and G on the boiling curve represents this transition regime. The size and the time duration of vapor films right above the hot surface increase significantly in this section. This greatly reduces the overall heat transfer from the solid surface to the surrounding fluid. Finally, the entire solid surface is covered by a stable and continuous vapor film, and the condition of film boiling begins. The point corresponds to the minimum heat flux is called the Leidenfrost point. Here, let's take a look again on the boiling curve with controlling the temperature of the heating element surface. Also, please be noted that the experimental conditions and discussions made for this curve are based on the presumption that the characteristic length scale of the bubble, which is defined as the capillary length scale, is much less than the length scale of the heat source or the hot surface. This length scale is also widely used in developing models for pool boiling. Here, sigma is the surface tension, G is the gravity, rho L and rho V are the densities of liquid and vapor respectively. The contact angle of a fluid during a heating process could be different from that in a cooling process, even on the same surface. For a weighted surface, the advancing contact angle is larger than the receding contact angle. As shown on the figure on the right, the liquid film with larger contact angle is thicker than that with smaller contact angle in the transition regime. Since the surface weighs better with a smaller contact angle, experimental results have shown that the heating process yields a higher heat flux at the same level of excess temperature. On the other hand, near the onset of nucleate boiling, the boiling curve is smoother in a cooling process since active sites may remain active below the required superheat. Therefore, the boiling curve may move from point D to point B with a continuous reduction of the heat flux corresponding to the reduced excess temperature. In other words, in a cooling process, there could be no sudden decrease in the heat flux as in the boiling or heating process. If the heating surface is subjected to a controlled heat flux condition, the path on the boiling curve is different from that for the temperature-controlled condition at multiple locations. At the onset of nucleation condition, the excess temperature jumps horizontally from point C to D to the left at the same heat flux, since the added mechanism of nucleation boiling tends to reduce the surface temperature of the solid. Another significant difference is that once the system reaches critical heat flux, further increase in heat flux leads to a sudden jump from point F to G on this figure. This means the temperature of the solid surface increases suddenly to a point that exceeds the melting temperature of most materials. Therefore, this point is often referred as the burnout point. As discussed in last lecture, by using a heating material with a high enough melting temperature, the heat flux after passing this critical point could be obtained. However, it should be reminded that, again, in most engineering applications, operating the system near to the CHF point is generally avoided. If the heat flux is reduced gradually from a point at very high excess temperature, the process on the boiling curve follows the path from point A to B, which is the ladder frost point. Any further reduction in heat flux lower to this value will lead to a sudden decrease of the excess temperature as shown from point B to C on this figure. This is resulted from the requirement that the heat flux is controlled, so the path cannot move upwards in the transition regime as in the temperature-controlled condition. In addition, with the active sites remain active during a cooling process as previously mentioned, the cooling curve moves from point C to D with a continuous transition, rather than having any sudden change in temperature. Eventually, the excess temperature is too low to sustain any active site of nucleation, and the heat transfer is only by natural convection. This is presented on the segment between point D to point E. As we previously indicated, the nucleate boiling is of great importance to a variety of engineering applications requiring high heat flux. Therefore, a number of models have been proposed and developed for predicting heat flux at a given excess temperature in this regime. Here we follow the discussion provided in the textbook to briefly introduce this kind of models, especially on the physics. The first one is the rationals model that was also discussed in our last lecture. In this model, it is postulated that the heat flow from the surface to the adjacent fluid is firstly treated as a single-phase convection. The agitation of the liquid flow behind the wake of departing bubbles contributes to the increased heat flux. Therefore, the convective heat transfer coefficient, or the Newton number, is proposed to be a function of Reynolds number and the Prandtl number, as in single-phase convection. This is shown by equation 1. The velocity term includes the latent heat effect. The characteristic length takes the effect from the bubble motion into account by using the bubble departure diameter. The empirical coefficient, CSF, considers the interfacial properties on the solid surface and is dependent on the combination of solid to fluid. It should be noted that the departure diameter decreases with reducing the surface tension, as predicted by the definition shown in equation 3. This trend was validated experimentally as described in the textbook. Finally, equation 7 is the form of the well-known rational correlation for pool boiling heat transfer. Here shows some values for CSF recommended for a variety of solid to fluid combinations. Values for R and S are also suggested. For further details, please refer to the textbook. The second model was proposed by Foster and Zuber. In fact, the basic form of it follows the rationals correlation, but the length scale and the velocity are determined by using bubble growth relations. For a heat transfer controlled bubble growth, the radius of the bubble is postulated to be in the form of equation 9. Noted that the Jacob number is a measure for the ratio of sensible heat to latent heat. The square root term on the right-hand side of equation 9 is the characteristic length for transient heat transfer in the liquid phase. By taking the derivative of R with respect to time, the velocity of the vapor to liquid interface on the bubble surface is obtained as shown by equation 10. Note that equation 9 is a time-dependent equation, so direct use of it for calculating R requires additional information. Equation 15 is proposed for evaluating the characteristic length to R, in which all parameters required are material properties, the temperature of the wall, and the pressure of the surrounding liquid. These properties are usually available for analyzing pool boiling. Another important thing to be noted here is that the temperature used for defining the Newton number is the temperature difference between the wall and the surrounding bulk liquid, rather than the standard excess temperature. This implied that the subcooled liquid would affect the heat transfer in the nucleate pool boiling. However, experimental data have shown that the correlations would fit better if the standard excess temperature is used, even for subcooled boiling. Detailed reasoning and explanation to this contradiction is provided in the textbook. The third model to be introduced here is the vapor-liquid exchange model proposed by Foster and Greif. The basic idea of this model is to postulate that bubbles act as microscopic pumps. When a bubble is growing, it pushes heated liquid from the near wall region into the cold ambient. When bubble releases or collapses, the motion and the vacancy left behind the bubble draw cold liquid to in contact with the hot surface. The process of each repeated cycle contributes to an exchange on the thermal energy with fluid at temperature of the average temperature of Tw and Tl, and the fluid with temperature Tl. Based on this concept, the heat transfer rate from the surface at an active site is given by equation 17. F is the frequency of the bubble formation and the release from the surface. If the density of the active nucleation sites on the surface is given, the heat flux can then be determined as shown by equation 18. One significance of equation 18 is that as the bulk liquid temperature decreases, the departure diameter decreases and the departure frequency increases. These three factors nearly compensate to each other, results in nearly unchanged heat flux with changing the subcooled liquid temperature. It should also be noted that increasing the temperature of the hot surface generally increases the number of active sites and the maximum radius of the bubble before departing from the surface. Also, in the textbook, two more models that share the similar idea of the convection-like model are provided, namely the natural convection analogy model and the inversed stagnation flow model. For more details, please check on the textbook. The last type of model for predicting the boiling curve is based on thermodynamic similitude. The basic concept is that liquid and vapor properties for different pure fluids can often be treated in a unified way if normalized with the corresponding values at critical point. In other words, the reduced pressure and temperature are adapted. This idea is extended to the transport properties in the nucleate boiling heat transfer. The heat flux in this case is predicted by relations with non-dimensionalized thermodynamic properties such as reduced pressure. Two correlations in this type are provided here for reference. The figure on the right compares four correlations that we have introduced. These four correlations can be divided into two categories: the model based on convection transport and bubble dynamics, and the correlation built on the basis of thermodynamic similitude. The latter one is of course easier to use since it requires only thermodynamic properties of the fluid. However, it should also be noted that the transport mechanisms and physical models are generally not considered in this kind of correlations. Another interesting phenomenon in the nucleate pool boiling is the effect of the hot surface orientation. Recall that for natural convection in single-phase fluid, for example air, the convective heat flux with hot surface facing upwards is generally higher than that of hot surface facing down. The gravity is pointing downwards in this discussion. However, as shown in Figure 10, at the same excess temperature, the heat flux with hot surface facing down is higher. This is resulted from two important mechanisms in nucleate boiling. The first one is that the thermal boundary layer thickness of the hot surface facing downwards is thicker, so the wall superheat required for the onset of nucleation is lower as implied by the Schurz model. The second mechanism is the sweeping effect of the bubble on the downward-facing hot surface. This sweeping of the surface greatly enhances the overall bubble release and the frequency of the cold liquid being brought into contact with the hot surface, therefore increases heat flux. In summary, we investigated and discussed about the characteristics of the boiling curve in more details. Important physics mechanisms and the corresponding transport phenomena are explained. Then, we introduced some classical models for predicting the boiling curve in the nucleate boiling regime. The concepts of those models are explained. It is recommended to refer those examples provided in the textbook for practicing the usage of those models and correlations.